Hello everyone and welcome to our discussion about adding nucleophiles to aromatics. We're going to see this is something we haven't seen before. It's different from what we've seen before for aromatics, but hopefully you'll find it interesting and you'll learn a few new reactions. All right, so the first thing we want to do is put this in context. So if you'll recall back previous in our semester, aromatics have always been used as a nucleophile before. So because they're a weak nucleophile, we were adding something as a good electrophile. These are called EAS reactions or electrophilic aromatic substitution reactions. So if you look here, we've got two different examples of EAS reactions. So the first one, if you recall, what are we going to add from the HNO3 and H2SO4? Right, we're going to add a nitro group, right? That's a nitration reaction. Exactly. All right, and the key electrophile for that one is the NO2 plus, right? If that looks familiar, that's the key thing we wanted to make. Okay, so then for the next one, what are we adding? Right, it's going to be carbons, right? We're going to do a Friedel-Crafts, that's a Friedel-Crafts alkylation, and so the intermediate would look like what? It's a carbocation, right? So this one has a plus here. This one can't rearrange. They can if that's a choice, but this one's not a choice. So we're going to add a carbon group. But there's one more thing we need to do before we can draw the second product. What is that? If you recall, I know it's been a while, but this is a good review. When you add the second group, it's going to matter where you put it. You can't just stick it anywhere, right? So it's going to be somewhere where there was a hydrogen, but we have to know based on the directing effect of the group that's already on there. So this is a director NO2, so then it's going to be an electron withdrawing group. So what kind of substitution will that give us? Ortho, meta, or para? It's a meta director, right? All the electron withdrawings are going to be meta directors except for the halogens. That's the exception, right? Okay, so hopefully that was a good review. Now we're actually doing something different this time. In this case, all the substitutions were substituting the electrophile for the hydrogen, right? But for these new reactions, we're going to substitute a leaving group like we've done in the past, but we're going to have to use something different. So if you recall, we said this way back in Organic 1, that you can't do an SN2 or an SN1 reaction on an aromatic. So basically, if I tried to add this directly, there's no way that reaction would happen. So that's not going to work. So we're going to have to see some special ways that we can make this reaction work out. So let's look at that next. All right, so let's think about some strategies we could do to make this reaction better. So the first thing we can do is maybe make a better leaving group. So if we have something that's really good at leaving, maybe we'll be able to get this reaction to work. Another option is we can make a better electrophile. So maybe it'll do something slightly different, but it'll still be a better electrophile. Or we can have maybe some sort of special mechanism that's not a normal substitution kind of thing. And remember now our goal is to have substitution on an aromatic, but instead of replacing a hydrogen, we want to replace some kind of leaving group. All right, so what we're going to do is find 3 different ways that we can make this substitution happen to replace a leaving group. All right, so the first type of reaction we can have is going to be called the Sandmeyer reaction. So as you can see here, the second type is called a SNAR, which is nucleophilic aromatic substitution. Instead of electrophilic, it's nucleophilic, right? And then the last type is called a benzene reaction. So we'll see what those look like. Now, it's important to know we're actually going to learn technically 4 types of reactions because we also need to know how to make an N2. So in my class, we haven't learned how to make this N2+, so we'll also have to learn how to make that reaction for me. Without further ado, let's continue and learn some of these reactions. All right, so the first reaction we're going to talk about is the Sandmeyer reactions. So the Sandmeyer reactions, there's also multiple of these, but they work because they have a really good leaving group. So N2 is a really good leaving group, as you can see here. It's leaving as nitrogen gas. So nitrogen gas is very, very stable. It's got a triple bond that's very stable. Also, because it's a gas, it can't return and start making the reaction reversible. So this makes it where it has to go forward and pushes the equilibrium forward. So that's another great thing. So N2 basically is the best leaving group ever. The other thing we can see about this reaction is it has copper in there. The copper is going to make it be an organometallic reaction. So some special stuff is going to happen for the organometallic part, but they're always going to have copper in the reagents, and then they're always going to have this N2 with the starting material. So let's look at the examples that we need to know for the Sandmeyer reactions. All right, so here are all the reactions. So if you look, there's 4. They all have this N2 plus, right, as the starting material, and they all have copper, but we're adding different things. The nice thing about this is if you know the product, you can almost what the reagents are going to be because they're really similar. So if you look, the halogens both have whatever halogen you're adding and then like the acid of that nucleophile. So HCl for the chlorine and HBr for the bromine. So that's pretty easy. And then for the cyanide, you don't have to have the H part. So you just have to have the cyanide part. That's easy. The OH one is a little bit weird because copper hydroxide is just not a very stable thing. So instead we use copper oxide, which is going to be here. And then we're going to use water as the place where we're going to get the H for the OH part. So that's where that comes from. So you don't have to know the mechanisms for these because they're organometallic reactions. The stuff that's happening is not really organic per se, metallic, and we don't know about the metallic part. So we're not going to have to know the mechanisms. You just have to memorize the reagents and what they make. So that's all you need to know for these guys. So as we said, you don't have to know the mechanisms for the Sandmeyer reaction, but for my class, you will have to know how to make a diazonium ion. That's the N2+. Now, if you're from another class, you may have already done this previously, so you can just skip to the end of this video. It'll be all done, and there's a part 2. But for my class, we haven't done this yet. It's the very last amine reaction, so let's talk about that now. All right, so for this reaction, it's actually going to be similar to things you've seen before, so it's probably going to be something that you could hopefully figure out, but I'm going to give you some key information first and then let you get a chance to try it. All right, so the main thing you need to know is about this reagent here, the NaNO2 and the H+. That's going to make an intermediate, which is sometimes shown as HONO, H-O-N-O. So the structure of that would look like this. It's basically a nitrite that has been, you just add a hydrogen. So it goes from being this to being with a hydrogen, right? So then from that, we're going to get a key electrophile. So the key electrophile looks like this. It's just NO+. And it's kind of like what we did a long time ago for the EAS reactions, remember? So hopefully it'll look familiar whenever we made the HNO3 plus the H2SO4 and we made it lose an oxygen. It's the exact same idea. It's just once we get our key electrophile, it's going to add to the nitrogen instead of an aromatic adding to it. And then after that, we're going to get rid of the final oxygen. All right? So let's look at this mechanism. All right, so at this point in the semester, hopefully you have some ideas of how to make things happen. So let's maybe talk through those a little bit, and I'll give you a chance to try part of it. All right, so we said the first thing we're going to do is draw our structure of the HONO, right? So we'll draw that over here. And then what we're trying to get to is the NO+. So that would look over here. So basically it's going to take us probably 2 steps to get that done. So what do we need to accomplish to go from the HONO to our key electrophile? Right, we need to lose an oxygen. So based on what we've seen so far, what's the best way to get rid of an oxygen? Usually it's to lose it as water, right? Usually it doesn't just fly off as OH or something like that. It's usually making water. So let's do that and then have the leaving group leave. So pause the video and see if you can draw those steps by yourself to get to the NO+, and then stop there and come back. All right, so now that you've had a chance to try it, is this what you got? Pause and check and see if that's what you got. These are the key steps you should have gotten so far. So what is the purpose behind these? Let's maybe outline it in case you're not sure or if you didn't get it quite right. So the first step, what are we doing? Right, we're going to make a better leaving group. And then the second one, leaving group leaves. Exactly. So that's how you get the first 2 steps. So now where are we going to go from here? So we should notice that anytime we're making a diazonium ion, we are coming from a primary amine. So we know we don't want to have a secondary or tertiary amine because then we would have to get rid of another carbon, which obviously we can't do because it has to be part of the N2, right? So the very first thing we want to do is have our nucleophile attack this key electrophile, right? So that's our next step. So that's going to look like this. And then what you're going to do is draw the product. Now, after you draw the product, I want you to think through what do you think the next steps are going to be? So the amine here has 2 hydrogens, and we need to lose those hydrogens. And then we're going to add the extra nitrogen, and then what else are we going to have to get rid of once we add that nitrogen? An oxygen, right? So how do we think we're going to lose the oxygen? Right, we're going to make water. Right, exactly. So there's going to be some acid-base steps, and I'm going to expect there to be some making a good leaving group leave, that kind of thing. So again, I want you to try it, pause the video, and then see where you get. All right, so how far did we get? Okay, so the very first thing we should do is this, right? So we're going to take off a hydrogen here, and we're going to add a hydrogen here, right, to make that better leaving group and make this not a leaving group. So then draw what that makes. It should look like this, right? And then we actually need to shift the electrons because we want to get rid of this positive charge, and we also need to eventually get to a triple bond. So how can we do that? what if we do a resonance structure to move the electrons around? So let's draw the arrows like this. So the reason we want to do this is to get to this structure up here. And this structure explains why are we going to take that hydrogen off the nitrogen, right? Before, if you look at the structure, if you look at the other structure, there's no charge on that nitrogen, so that would be, we would think that would be pretty hard to remove. And so now we see, oh, it's got a positive charge, that's going to be a lot easier to take that hydrogen off in an acidic environment since we don't have a strong base. Right, perfect. And now also it's going to be where we can add another hydrogen to the oxygen. Before, in the other structure, you can't add a hydrogen to that because it's already got a positive charge. So we need to get rid of the positive charge so that we can do that. All right, so from this structure, try to draw the last steps to get to the product and pause the video again. All right, so is this what you got? Right, and then we do this. All right, so then let's go back and label why we did all these steps. So I already said these steps back here were to make not a leaving group here, right? Make a better leaving group here. And then this is, we'll just call it resonance. We'll just call this resonance for now. It's basically to get the double bond that we want. We can just call it resonance. Then this one, what's the point of this H plus part? Right, so let's make it not a leaving group and make this other one a better leaving group, right? And then what's this very last step? Leaving group leaves, exactly. So then that's our whole mechanism. So again, we've done a pretty complex mechanism. If you look, it's got about 7 steps that we drew, and it's all using steps that we've seen before, except maybe the resonance step, that's new, but all the other ones should be things that we've seen before. The first part was similar to our aromatic section, and the last section is what we've been doing a lot, right? Making things good leaving groups, making things not leaving groups. All right, so hopefully that makes sense. If you have any questions, just let me know, but definitely practice it. And with that, we're going to stop our video here, and we'll do the second half of our last aromatic stuff as a part 2 video. So make sure to check that out.